Well, wait. First off, homework. Study. Study. Train like you fight. Remember, I was like saying in the Army, we train like we fight. Meaning, in particular, with this one, you're going to have questions that are exactly like sections 8.1 and 8.2. And I will not give you anything in minutes. I will give you stuff in degrees with point something, right? So decimals, with degrees and decimals. And so practice that way. Like when you do one of these, I'm just going to say, go through sections 8.1 and 8.2, grab a random one, and pretend that you're doing it in here, right? Use a calculator, keep as many significant digits as you possibly can, and I don't care for you to round them off at the end. Just give a bunch at the end, right? Although, if you're writing stuff down on your way there, you don't need to keep all of them with every single calculation, but keep them in your calculator. Right? Keep as many digits as you can in your calculator. And then at the end, just give me we'll just say 4 digits. We'll just say 4 digits all the way across, like at the end, for each of the answers, for each answer that you give. Yeah, let's just standardize that, 4. Because this is not a chemistry class. If this were a chemistry class, we would be very, very concerned with how many digits we report. This is not a chemistry class, so we're just going to... I want to instill in your mind to try to keep as many digits as possible because rounding error is a real thing. One thing I wanted to say before I jump to questions is I emailed this out, but I wanted to be explicit about it. And I'm not using my notes, so I actually wrote something down. Let's say we're doing a side. And you're given A equals, 20, B equals, 15, and C equals, let's say 10. 10? Yeah, that would work. That would be a triangle. Notice if I said C equals 1, that could be a triangle, but maybe a triangle. But if C were 1,000, you could see right away that couldn't be a triangle.
Yeah.
Right? But anyway, my point is, let's say we're doing that. This is obviously a side problem. And I'm just going to say solve the triangle. In fact, I'm not going to print anything out. I'm just going to write it up here. This is going to be your quiz. I'm going to say solve the triangle, and I'm going to give you a bunch of these types of things. One might be like alpha and beta, and then I give you one of the things. I might give you alpha and 2 sides. I might whatever, right? All of the different things that we've done up until now. And what I was saying was, and I wanted to cover this, and I just completely slipped my mind. It's like, okay, we have a triangle, ABC. And let's just call this side A, there's 20. And this one's 15, so it's not quite as long. And then there's 10, so whatever. There's this, and there's B is 15. It looks something like this. And the question is, I didn't bother to tell you this, but there is a best way of going about doing this. You want to start by finding, because obviously there's 3 angles to find. We're looking for gamma, we're looking for beta, and we're looking for alpha. And in class, I kind of made it sound like choose any one that you want, but I completely forgot that there's utility to choosing one of these. And the thing is, you want to choose the one that's opposite the longest side. Right? Why is that? Well, if we do, and let's just do this, right? So I'm going to say, okay, side. We got to use log cosines. I want to use alpha, so I know it's going to be something cosine alpha. And it's going to be a bunch of stuff, but alpha pairs with a, so it'll be a squared. And then it'll be the other ones, b squared plus c squared minus 2bc. There you go. That's what we want to use. The reason why is that when you solve here, you get a squared minus b squared minus c squared all over negative 2bc equals cosine gamma. Now you take the arc cosine of this, arc cos of all this stuff. There's two possibilities. If this is acute, well, it's acute, and so are all the others. Because gamma, what am I doing? Alpha. Minus 5 points for today for not catching that, Noah. I mean, sorry, Victor. Alpha, there we go. Alpha is got to be the biggest of the angles, right? And that should be obvious because if this is the longest side, then that angle has to be longer, or it has to be wider than any of the others. Okay, so if it's obtuse, then none of the other ones can be obtuse either, right? So in any case, if this thing's acute, well then so are all the others. If it's obtuse, so are all the others. But then the reason why that matters is because now, after you find what alpha is, you're going to use law of sines for the other ones. But then when you're using law of sines, remember, you might end up with an acute and an obtuse case, right? Because we've said before, if you're given, say, alpha equals, 30 degrees, and you're given A equals, say, 5, and B equals 1, well, now you're in the domain of here's your alpha, here's your beta, here's your B and your A, there's your alpha. Now you're using law of sines, but there may or may not be an acute case and an obtuse case, right?
Yeah.
And so you might run into that. You might very well have a side where you do end up with it. There's no way around it, right? Like let's say I solved all of this, and let's say that it came out to be that there was an obtuse case and there was an acute case. So here's one of them, here's the other one, and so then we had two possibilities for C. Either C was this length or C was this length. I could have given you one of those up here. And it could have been the case. Actually, could it have been? I'm not too sure. But the thing is, you would have to check. You wouldn't know, and you'd have to check if you chose one of the acute angles first. But if you choose the biggest one, and it turns out to be obtuse, another thing is, with this, you're with law of sines, you end up with something like sine theta equals some junk. You do the inverse of it, and you get arcsine, some junk. And the problem with arcsine is that it's only going to pull back values here, right? So like if all of this ended up being 1/2, then there'd be two possibilities, and you'd have to check both possibilities, right? Cool thing about arc cosine, think about what the cosine function does. Every possible value that you could get, it's going to be what it will give you values between 0 and pi, right?
Yeah.
So you don't need to go and think, well, wait a minute, what is this one or is this that one? It's just going to give it to you the way that it is. So by doing this, if there is an obtuse angle in there, you found it first by choosing the largest side to use here. Then if that's obtuse, you know the other ones aren't, and so you're good to go. Or even if it's acute, you know the other ones aren't obtuse, so you don't need to go through and do this when you're doing law of sines. So that's one of the I meant to say that, it completely slipped my mind. I didn't have it down in my notes, but there you go. So, and that was all I wanted to talk about before I got to specific questions. Do you have any specific questions?
I have a couple. Yeah.
Okay, cool.
If you did the same thing where you put like a triangle on the x and y coordinates, and you use tan, could you find law of tangent?
Ooh. Okay, so here's a question. You do the same thing where you put so let's put a triangle on the x and y coordinates and try to see if there's a law of tans. I wonder if we could derive one. Let's find out. So, let's start with some triangle. There's some triangle. We'll call this alpha, meaning A. We'll call this beta, and we'll call this gamma. C. And we want to see, can we come up with some kind of law of tangents? So let's see. Well, tangent, let's just see. So here's a height. We're going to call that height h. And so let's just take tan alpha is h over, ooh, man, here's the problem. We don't know what c might be or might not be. This could be why there's not a law of tangents, but let's call this k is h over k. And now, yeah, but here we've split gamma, and so it's not quite gamma, and it's not necessarily half, because if this thing is really wonky like that, you won't be splitting gamma in half when you go perpendicular. But one thing we can say is that this remaining bit right here is c minus k. And so we could say that tan beta would be opposite over adjacent. So tan beta is equal to h over c minus k. So that, and now let's do the same trick, because again, I've never done this before. This is a completely novel question. We didn't coordinate ahead of time. So maybe we'll figure something out. But what I'm doing is the same kind of trick that was done for the others. So k tan alpha is equal to h, which is also equal to c minus k tan beta. And so we have a k tan alpha equals c tan beta minus k tan beta. And so let's get this over here, and we have 2k tan alpha is equal to c tan beta. But then again, we don't know what k is. So is that helpful? One thing we could do, actually, since that's a b, we could say that this bit right here, if we go cosine alpha, that's equal to k over b. So that k, this looks like it's getting more complex. Actually, ooh, wait, hold up, wait, just a second now. B comes upstairs, and we get b cosine alpha equals k. So I'm going to substitute that in for k, and I get 2b cosine alpha tan alpha is equal to c tan beta. But cosine alpha, tan is sine over cosine, right? So then the cosine in the top cancels with the cosine in the bottom, and we get 2b just sine alpha. So it's not quite a law of just tangents. So this could be why there's no law of tangents, right? Like that it's not just something crisp and clean. But that's not to say that this might not be useful in some scenario, right? Like perhaps if you know what C is and what beta is, and you're trying to find alpha, you know C and B, although, but then, yeah, and it's not, this doesn't look like something that's easy to remember either, right? So that could be why. I'm sure though, I mean, maybe if we played with this a lot more, maybe we could find something that's simple and easy to use. But I've never heard of a law of tangents. This could be why, right? That the reason why law of sines works so well is because sine has something to do with this as a hypotenuse, right? Same thing with cosine. But tangent doesn't use a hypotenuse at all. It uses these two unknown quantities, which change regardless of, with these angles. And so, yeah, that could be it. But maybe there is a law of tangents out there. Something very succinct. I just don't know about it. All right, more questions. Is there any problem you want to go over? I'm going to check my email to see if Noah's emailed yet, or if he's going to all. I checked just before, but let's just make sure. Nothing from Noah. Okay. So, nothing?
For the Pythagorean identity, since it was derived from a triangle, you couldn't have cos of 180 degrees in it. As if
Wait a second. The Pythagorean.
sine squared plus cos squared equals.
Okay, so sine squared, we'll say theta, plus cosine squared theta equals 1. Okay, now what were you saying?
If you subtract off sine from both, yeah.
So bring sine over to this side.
Yeah.
So we have cosine squared theta equals 1 minus sine squared theta. Okay.
And if you take root,
Square root of both sides. So we're going to take the square root of both sides. This gives me cosine theta is either plus or minus, depending on which one. Okay. Now what are you saying?
if cosine were theta were 180 degrees,
If it were 180 degrees, or let's call it pi.
pi.
So first off, let's look at this. So there's a couple different ways we could look at this. I'll look at this as many different ways as we can. So here's pi, which is 180 degrees. The output of cosine there is -1. This is cosine theta. There's theta. And so if you plug in a pi, you get a -1. But remember what this plus minus does. Right? This is the same kind of thing here. Now let's do it this way. This is the same thing as y squared plus x squared equals 1. Right? And so then when I go x squared equals 1 minus y squared, and we know that this thing, this object, is a circle of radius 1. Right?
Yeah.
And so then when I do this, in fact, like, yeah, I'm using cosine as x because cosine is the x coordinate on a circle. But so I was trying to stay with that, but just to make our brains hurt a little bit less, I'm going to do it the other way. Just so you could see, because I don't want to bend our brains too much. I want to do this in the way we usually think of y as being an output. And so I'm just going to do it this way. It doesn't matter which one I chose, really. But now, okay, so that's still true. This still defines the same circle. But now when I take a square root, what happens? We have to do a plus or a minus. And what does that look like graphically here? Well, this means that we have two possibilities. That y is either equal to the positive amount, or it's equal to the negative amount. And in this case, what we're talking about is the top half of the circle. And in this case, what we're talking about is that bottom half of the circle. So like if you were to just graph the function y equals this, it would look like this. It would go through here at 1, it would go through here at 1, here at -1. If you graph this, well, it's just negative of that thing. It flips it down, so it's this. It goes through here at -1, -1, and 1. Okay, so what's going on here? Well, it's kind of the same thing. You're talking about that cosine, the value of cosine, is either going to be, depending on where you are, it's either going to give you the positive or the negative of this. And so what you're talking about then is, and you could kind of see when that's going to happen. Like here you could see it because you're like, when is the y value going to be positive? Well, it's going to be whenever you're talking about the top half of this circle. When's the y value going to be a negative number? Well, it's whenever you're talking about the bottom half of this circle. This is a little bit different because we're not so much talking about a geometric object that you're splitting into two bits. But what this does is this says, Well, and I could just look here and say, well, cosine theta is going to be positive whenever you're between 0 and pi over 2. And then again over here from 3 pi over 2 up to 2 pi. So you could say, in the same way you said before, what part of the plane is this true on? Well, this one's true on the top half. This one's true on the bottom half. Here, you're kind of saying, well, whenever theta is from here or here, these are the two cases where you're going to get the positive square root, 1 minus sine squared theta. And whenever you're here, where it's actually negative, this is where you're going to use the negative 1 minus sine squared theta. And so you said, well, what about pi? Well, I'm going to look here and say, well, I know that at pi, cosine has to have a negative output, so I'm going to use the negative one. So now that I'm plugging in pi, I have to select which one to use, the positive or the negative. Knowing that cosine's negative in this range here, or in this domain, then I'm going to use the negative one. So I'm going to say it's going to be negative square root of 1 minus sine squared pi. What's sine of pi?
0. Should be
0.
negative 1 equals 0.
And so, yeah, so it's going to be negative square root of 1 minus 0, same thing as negative square root 1, which is just negative 1, which is what that is.
But if you didn't take plus or minus,
If you
then
didn't
you
take
would-
plus or minus, then you're missing out on half
should
of
be
it, right?
negative
It would be like solving for this, and then forgetting to do this, and then what you've ended up with, and you're like, what object do I have? Oh, you have this. Well, no, you forgot about the other half of it, right? So that's kind of what's going on here. It's only like we're talking about now. It's different because we're not. Well, because like there's a variable inside each of the y and the x, right? This is kind of like saying you have some function y of theta squared plus some other function x of theta squared. And so it's a little bit different than just talking about where on the plane just a x is a coordinate and y is a coordinate. Now you're saying we have two functions that do this crazy thing, and now you have inputs to those functions. It's a little bit different. And the way that looks is now we're not just splitting apart one object. Now we're saying, well, you got to kind of use your brain and say, this works, but you have to think, you have to know kind of ahead of time, when should this be positive and when should it be negative? And so knowing that here at pi, it should be negative, then the one I need to select is the negative one.
Yeah.
But if you fail to do that, you're missing half of this picture, right? You're missing all of this, you're missing all of this right there, and you're going to get junk, right? Because if you had forgotten to do that and you just said it was positive, you would have done this, you would have got that, you would have got that, and you'd say, oh, cosine of pi is 1. But that's because you forgot that, well, wait a second, you have to, just same way here, right? Like, when x is 0, what should it be? Should it be 1? Well, it depends, but you know, like you're on a circle and you say, what should the y value be whenever x is 0? Well, it depends. You're the top half or the bottom half, you know? And so, there's kind of the same thing here.
Doesn't the equation for a circle relate to sine squared plus cos squared?
Yeah, that's how we got all
That's
this.
how we go. Okay.
Yeah, because we said that the way we're defining sine and cosine is we take the unit circle, we take a theta, right, and you have some x value, some y value for any point on here, x comma y. And then we said, well, it's the unit circle, right, and so that means that the radius is 1, and therefore sine theta is equal to opposite over hypotenuse. Opposite is the y, whatever the height is. Y divided by 1, and so sine theta is just y. And so yeah, it's that coordinate right there, right? And so that's kind of what I was saying here, right? Like you take that, and so x comma y is the same thing as cosine theta comma, sine theta. And so that's how they're related. It is the unit circle. These are the functions that we call parameterize the unit circle. We have a parameter, which is this, the input value. So, whereas when you just have this, you just have a collection of points. And you say, you know, like it's okay, well, that's just it. It's just a circle. But with this, we could parameterize that and say, for every point, we could assign a certain input value to it. We could say that when that input value is, say, pi over 4, we could say that, well, this is the point you're talking about. Because you kind of think about this as going along, as a point going along the unit circle as you change the parameter. Right? Does that make sense?
Yeah.
And so, yeah, so when it's theta, when theta is equal to pi over 4, you go from 0 up to pi over 4, your point has traveled from here up to here, and so on and so forth. And these actually give you the coordinates of that. It should be 1 over square root.
Is that like the polar coordinates?
We're gonna, it's, yeah, so this is polar coordinates. That's one of the things we're gonna go into next. We're gonna do we're gonna do vectors first, then I think after that it's polar coordinates. And that's what we're gonna talk about. Like, I could tell you to go to the point, root 3, comma 1. I could tell you to do that. I could say, you go drive root 3 units east, and then go let's say root 3 miles east and 1 mile north, and you'll get to my house. Or I could tell you, well, I know what this is, right? If that's root 3 and that's 1, what does that length have to be?
Root 3 squared plus 1.
This is a triangle you should know by heart by this point.
Oh, yeah, 2.
It should be 2. And you could check that by squaring root 3, squaring 1, and taking a square root. Gives you 3 plus 1. And my handwriting's terrible today. Root 4, which is 2. Yes, okay, so that's 2. That length is 2. And what angle must that be?
Pi over 6.
Pi over 6. Good. And so I could tell you, you know what? Look east, and then go pi over 6 degrees this way, and then go 2 miles that way. Again, in one hand, I needed 2 numbers to describe a point in the plane, right? 2 coordinates. I needed an x coordinate and a y coordinate. And so we call these Cartesian coordinates because we're talking about a Cartesian plane. Those are my x, y coordinates. Or I could give you what we call polar coordinates, which is the same point, but now to describe it, instead of going x, y, I go angle magnitude. And so that would be the point pi over 6 comma 2. Conversely, if I had started by giving you this, say, hey, go to this point where you go from the x-axis, go up pi over 6 and go root 2, you'd say, okay, you told me to go to that point right there. Now I ask, where is that in Cartesian coordinates? You go, oh, wait a minute, that's a pi over 6. I know this triangle. That's pi over 6. That's 2. Oh, that fits. So that's a 1, 2, square root 3. So there's 1, 2, square root 3. So the distance from there to there is 1, which means that coordinate is 1. The distance from there to there is root 3, which means that coordinate is root 3. And you could recover your Cartesian point. So really, these are the same things. You're talking about the same point in 2 different ways. Right? So, yeah, we're gonna do that. We're gonna really do that. We're gonna do that until you're sick of it. So good. Yeah. Okay. Cool. Did that answer your question about that? Yeah. It comes down to, like, it's not foolproof, right? And when you do this square root thing, you have to know, well, wait a minute. And in different contexts, it means different things. Like in this context, it means, well, there's either the top half or the bottom half. In this context, it's a bit more tricky. But you have to know, like, well, where should cosine be positive? Then I want to take the positive one. Where should it be negative? Well, that's where I want to take the negative one, and so on and so forth. So it's not just foolproof. It's not like we can't. Well, you could plug it into a computer program, but you have to teach the computer program to do this thing. You'd have to teach the computer program, well, if your theta is in this interval, do the positive one. If it's in any other interval, do the negative one. And so that's a pain, but this works really well. I'm glad I brought this. Oh, how sweet. Okay, other questions?
No, I
Don't have any other questions. All right, then let's do an example of something that you'll see on the quiz. Okay, this very well could be something that you see on the quiz. You walk in, and I'll say something like this. I'll have them numbered. And one of the things you might see is something like this. And these are, yeah, those are degrees. Okay.
You can use law of sines to find alpha.
Law of sines. Okay, so let's see. First off, I notice that I'm given two sides and one angle. And crucially, that angle is opposite from that. That's the key there, because if it were beta, in fact, I think we'll go through and do and change it to beta and see just how different this is going to be. But what I like to do is to draw this thing out. So that's where I'm going to start with this. I'm going to say, okay, gamma is the given thing, so I'm going to do my gamma right here. There's gamma. And then we have the opposite side of gamma, which is C, right here. And that's 20.24. Now, it doesn't matter either way, because I could flip this if one of them's wrong. So I'm going to choose this to be A right here. 17.31. So if that's A, that means this is alpha. And then this thing must be beta. Now, there's a problem, because this is the angle side-side. Do not forget, this is an angle side-side. So that means this we're going to have a lot of work to do. So I'm going to get my calculator. So you already said use law of sines to find alpha. And I like that, right? Because we could say sine of this is to this. So sine gamma is to C, which is 20.24, as sine alpha is to 17.31. I'm going to go ahead and do this. Get the thing that I want by itself by getting my 17.31 up here. Sine gamma. Gamma's given, I'm just not writing it down. And then that guy stays in the bottom. That's 20.24. Equals, now I could write sine alpha, but I know what I'm about to do. I'm about to take arc sine of it, so I'm just going to go ahead and do that. Arc sine of all that stuff. Now, let's see what my calculator tells me. Arc sine of 17.31 times sine gamma. Gamma is 73.01, close parentheses, Now divide by 20.24 in parentheses, and I get that alpha is equal to, did you get it?
I got 54.87.
That's what I get. Good. 54 point. I'm going to go 876. But it doesn't really matter. Like, it is good. Like, you know, I say to keep a lot of decimal places. Really, I'm just keeping them in here. But it is nice. I just, as a habit, write a bunch of them there. Because what if I'm doing something else and I get something that's 54.8? Something. They just happen to be very close to each other, and then I'm like, oh wait, which one was that? If I had just carried it out a couple more decimal places, I'd be able to differentiate between these two. So that's what I just, as a matter of habit, that's what I'm doing. But that's not the whole story, right? Because it might be the case that it's like this, and then alpha is a acute angle, or it could be that this is what's going on, right? It could be that there's alpha, here's gamma, and here's beta. And if that's the case, then what is alpha?
It'd be 180 minus.
Yeah, right. Because what we actually did here is we said, okay, we have some number, whatever it happened to be. And this is the sine function. This is sine theta. We had some number. This is the 17 sine blah, blah, blah. And it's whatever it is, some number n. And we asked arcsine, well, what is that? And it told us that alpha must be 54.9. But there's another possibility, right? It could have been. That's not sine. That's not what sine looks like. Sine doesn't look like that at all. Sine it's like, wait a minute. Wait, I have to add to 180? Wait, what's going on? Sine looks like this. Math teacher. Sine theta looks like that. And so we had some number n. We plugged it in and our calculator told us, the degrees you're looking for is 54.9. But that's not the whole story, because that's assuming that it looks like that. It might be like this, so we have to find the other one right here. And the way we do that is we say this distance is the same thing as that distance. This value is 180, so I go 180 minus that thing. 180 minus, no, I'm just plugging it right back in from what I got. I'm not typing anything in. It is, what did you get?
125.123.
125.124. There we go. Okay, so now, all right, we got, from there, I guess we just need two more things, right? We need beta and we need b. In the first case, what's easier to find, beta or b? Beta. Because all we need to do, right? If we have two angles, we can find the third. And that's too easy, right? So that's what I'm going to do. I'm going to find beta first. I'm going to say, okay. Beta should be 180 minus alpha minus gamma. And so that's 180 minus, I'll do gamma first, 73.01. Minus alpha, which is the 54. So I'm going up to the 54. Plug that in. What did you get? That's what I get. 52.114. There's that. Okay. Now, we have alpha, we have A, we have gamma, we have C. All we need now are beta, which we have, so the only thing that's left is B. And so the way I'm going to write this out, again, law of sines, because I know I'm looking for B, instead of going sine beta over b, I'm going to go b over sine beta equals, and I want to use, I guess either way it doesn't matter because we had to derive c, or no, c is given. Oh, c and gamma are given, so I want to use those.
Yeah.
Sorry. So I'm going to use c, which is 20.24, over sine gamma. Gamma is 73.01 degrees. That would have been divided by sine of beta, so I'm going to put sine beta up top. Sine beta is 52.114. Okay, so then b is equal to 20.24 times sine 52, the one that I just got, so I'm going to go up 1 and get it in my calculator, in parentheses, divide by sine 73.01. What did you get?
$16.703.
There we go. There we go. So let's make sure that we got everything. Now that I have it, we have alpha. And please box these as you're doing them. And like, I'm not going to make you label them all here. It'd be cool if you did, but it's a quiz and we're rushing, so I don't blame you if you just plug along with it. So we have those three given. We have the 1, the 2. I didn't box this. We need to box that. And the 3 that we didn't know. Now we have our, moving over to here, we have alpha. A is given. C is given. So again, we need to find the same ones. If we know alpha, we know gamma, we can find beta, which is 180 minus alpha minus gamma. So 180 minus, in this case, alpha is the 125, so I'm going to go up until I see my 125, 1, 2, 3. And then minus off my gamma, which is 73.01. And what do you get?
I got negative.
Yeah, so what does that tell you? Tells you that with these lengths, in order to make this happen, the triangle you'd have to construct would look like, instead of now, like on one of them it works this way, right? Because it's 20, so it's longer. Now you'd have to bring it all the way out this way for it to work. But that's not the triangle we're looking for, right? So when you see a negative angle, now we're outside of the realm of things that we need to worry about, and we are not. We're done. We're done. And it would be cool if you could just say no triangle. Or no obtuse, like this is the obtuse case, and you could just say like no obtuse case or whatever. But let me know that you didn't just run out of time and you didn't know what this meant. Like, please let me know here. Like, no, just say something. Like, I'm done. Like, I understand that such a triangle is not going to work. Yeah. So, okay.
So for the obtuse case, do you have to try to find it just for angle side or for everything to do?
Well, if you're doing law of sines and you have an angle, so the thing is like it could come up when you're using some kind of law of cosines with something. And then what you have is you know this angle, you know this side, and you know this side. And so now you're in this scenario where you'd have to do that. And once you know another one, so it might come up, right? But it's whenever you end up in this kind of scenario. When do you not have to do that? Well, when you know two angles, you know the third, right? So if you're given angle side, or angle or whatever, right? Whatever those distinctions were, then you don't need to worry, right? When we talked about when you have side, just do the biggest one first, and then you don't have to worry, right? So then what we're about to do is I'm going to change one letter up here. And we're going to end up with angle side angle. Or, sorry, side angle side.
So you have to use cosine.
And then, then we'll need to use law of cosines, and then let's talk about what the possibilities are, given any given lengths. And so then we'll see what we have to do. Okay, so I want to turn this into a side angle side. So let's make this a B. So same numbers. Only now this is a B. And so let's draw it out and see what happens. Gamma is between A and B. And so I could just draw, I'll make B a little bit longer, A a little bit shorter. Here's gamma. And actually, if I were drawing this correctly, this looks like a 45-degree angle. It would need to be pretty wide, but I'm not too worried about that right now. So let's call this one A and this one B. This is B is 20, 24. A is 17.31. Now, can't use law of sines because there's nothing across from here, so we have to use law of cosines. And let's talk about that. So this, the opposite side to this, should be like this. And we can kind of see from the setup that these have got to be acute, right? Like, since, I mean, just by they're almost, they're very close to the same length. But let's say we didn't know that, right? Like, maybe one is the obtuse case, one is not, whatever. The only recourse we have is to find this length right here. And so that's C. So I'm going to use C squared and then stuff, cosine gamma. That's where I'm going to start. C squared is equal to A squared plus B squared minus 2AB cosine gamma. And so C squared is equal to, and I'm just going to plug all this into my calculator just right now. And see what we get. So, A is 17.31. I'm going to square it. Add that 2 to 20.24. Square it. Subtract 2 times A is 17.31 times B is 20.24 times cosine gamma is 73.01. And I get, what do you get?
I got 22.46. 20.
I got that.
Yeah.
And then you take a square root. And you're going to get, let's see, so square root of that stuff. Not rounding anything, I'm using everything that we could have as 22.4620. Okay, so now what realm are we in? Well, we have 3 sides, and I could just kind of tell here. 22.462. I can kind of tell, just by the way I've drawn this, that yeah, if this is 20.24 and that's 17.31, and really it's going to be a little bit higher. It's going to look something more like this. You can't really have an obtuse case since these are almost the same size. Like, I don't know, actually maybe you could. Maybe you could. Maybe it goes like that and you could bring it back like that. Maybe you could end up with an obtuse case. I don't feel like I should. But now I'm kind of in the realm of that. Because now I have an angle, a side, and a side, which is the pane and the angle side. And so I'm going to have to kind of stop and think about that. But what I could do, another thing I could do, is notice This is the longest side, right?
Yeah.
Once you know all your sides, just take note. What's the longest side? That has to be the biggest angle. Can you have an obtuse angle? No, because if that's the biggest angle that there is, and it's acute, you can't have another one. So this can't happen, actually. And so, and another thing to notice is like, yeah, maybe you could make one that comes all the way back, but then like 20, this is longer than that, right? And so, that's not a very good argument. But like, this is what you do, and this is why I should have said this last time, is that this is so useful. Once you know all the sides, take note of what's the longest one. That's the longest one. Therefore, that's the biggest angle. Now, if that weren't the case, right? If this were, say, 17, and this were 22, well then, that's the biggest angle. It might be obtuse. I don't know. And one thing you could do for all of these, like, now that you have three sides, you could just law cosines every single time. Law of sines is faster, but the cool thing about law of cosines is you never have to worry about whether or not that's acute or obtuse. It'll tell you whether or not it is. And so, maybe you wanna weigh that in. In fact, let's go ahead. Let's do it both ways right now and see just how much of a pain it would be if we just brute force. Once you get three sides, just brute force and use law of cosines. So let's do it the old way, where we're going to use law sines now. Of course, then we're going to have to use our brain to make sure that we don't have to deal with an obtuse case. So let's call this alpha and this beta. And I'm going to use these two, I guess. So sine gamma is to C as sine, let's go, alpha is to A, but instead of writing it down here, I'm going to bring them upstairs. Right? You comfortable with that? Like, I'm just kind of skipping one step. The next thing I would have done if I'd written it down there is bring it up. And so now, okay, that means that alpha is arcsine of this stuff. If you do that on a test, I'd be perfectly happy with that, as long as you get the right answer. Arcsine of sine. Oh no. Arcsine of. Ooh. I'm trying. Your calculator is probably different, but if I try to press sine again, then it does something else. So I'm going to do the 17.31 first. 17.31 times sine gamma is 73.01. 73.01 end sine. Divide by the 2246, which is in my calculator, so I'm going up end parentheses, and I get alpha is equal to 47.476. 0.476 degrees. So there's my alpha. There's that. Okay. Now I just need beta. Same setup as this, right? We know that sine beta is to be as sine gamma and all that, 22.462. But now beta is opposite 20.24.
Can we just go 180 minus alpha minus gamma?
Oh yeah, thank you. So you do it that way, I'll do it the hard way. Thank you, arcsine. Yes, thank you. Please do it the smart way. So arcsine, but now I'm curious. I want to do it this way. So 20.24 times sine gamma is 73.01. Divide that by the 22.462, which was up here. What'd you get? 59.5. That's what I get. 514. Yeah, do it the smart way. Don't do it that way. But the problem is when we got to here, we'd have to stop and go, whoa, 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 wait a minute. I just used this and this and this. That's angle side side. Is it possible that there's an obtuse case? But then you stop and say, wait a second. This is the longest side. That thing's not obtuse. So none of the other ones could be obtuse. Everything else has to be smaller than that, because the opposite to gamma is the largest side. So I could say alpha must be smaller than gamma, which it is, and beta must be smaller than gamma, which indeed it is. So now I can feel confident that I haven't missed any cases, and I'm good to go. Now another thing we could have done, another way we could have done it is just brute force. Once we get this, now we have side, 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 and we could just brute force everybody and say, well, we did c squared. Let's do a squared this time. A squared. Oh no, wait. We know a. We know a, right? Oh, what? Sorry. A squared plus b squared plus c squared minus 2bc cosine alpha. And now we're going to get the cosine alpha by itself by doing a squared minus b squared minus c squared divided by negative 2bc equals cosine alpha, so that alpha is equal to arc cos of that stuff. And let's do that, arc cos of. Now this is the hard part, is that I got to use parentheses. I'm going to do this when I plug it in. So I'm going to go parentheses. A squared is 17.31 squared minus b squared is 20.24 squared minus c was the one that we got. So I'm going to go up and grab him. He was 22.46. 22, up there he is, 22.46. Take it and square it. End parentheses. Divide by parentheses. Negative 2 times b was 20.24 times c was the one we just derived, which was the 22. So I'm going to go back up and find my 22.46. There it is. End parentheses. End parentheses. And that should give me alpha. And it tells me it's 47. Sweet. So, alpha is 47.476. And then we get beta by going 180 minus alpha minus gamma, unless you want to do what I did. And so, is this quicker than that? Not really, but you see, there's always trade-offs, right? You could go faster, and yeah, I feel like I personally am more familiar with this, right? You could go faster here, you could get that. This also is kind of clunky. You have to make sure that unless you're doing this one little bit at a time and then doing like say you go a squared minus b squared minus c squared, enter. And then you go minus 2 times b times c, enter. And then you take those two and divide them by each other. And then you take the arc cosine of that. And so you're doing a bunch of things there. There's a lot of calculation to be done with this method. A lot of places to mess it up. Like I easily could have put a parentheses in the wrong place or forgot the negative like I've done 1,000 times. Forget that negative there. And so there's more places to mess that up. But on the flip side, you never have to worry about whether or not you're getting a acute case or whether you're doing the acute case or the obtuse case, because arc cosine will tell you. So there's trade-offs, right? Like here you have to stop and go, wait a minute, is it possible that there could be an obtuse case here? Well, such and such and such. And so really you end up doing about the same amount of work. One of them is just more in your brain using logic. The other one is I have to punch this in and make sure it's really, dead on. So
can you look at this? I think it's giving me an error for...
Uh-oh. Minus... Okay, so you did arc cosine of that
and that's your arc cosine. So there's your top parentheses. There's that. Divide by. Yeah. That right after your divide is where you need the parentheses.
Oh.
You did -2, and then you did parentheses. No. You do, there, I'll show you like this. So you go arc cos, parentheses for the top, 17.31 squared, minus 20.24 squared, minus the 22, oh, can you not go up?
I think, yeah, I just have to just write them down and type in as many.
Yeah,
as I
well,
possibly
sorry about
can.
that. 22, well, that's good that you do that. So 0.46203 squared, end parentheses. Now, you're dividing by, you want the entire denominator in parentheses. So you're going to go parentheses, -2 times 20.24 times 22.4620 end parentheses. Now you've ended parentheses on the bottom. Now we're going to end parentheses for cosine, or arc cosine. And that should do it. Okay, there you go. So yeah, careful with that. Although, spending that time to get used to that will make your life in like college chemistry so much easier. If you could just put all of that in like with parentheses, if you get good at that, you've like really bought yourself a lot like moving forward. So it's this is good practice, you know, but at the same time, there's a lot of places, just like you saw, right? It's like, well, what was my calculator doing? Then you got to go in and do it all over again. So there's that. But then, on the flip side, you don't have to worry about whether that's obtuse or acute.
Yeah.
So there's trade-offs and stuff like that. So, okay. And I think we got everything, right? We got beta, we got alpha, we got beta, we got alpha. We found C in both cases, so yeah. Okay, there's that. All right. Any other questions?